All right, so the last section of this chapter has to do with molecular orbital theory, also known as MO theory. So MO stands for molecular orbital. And so everything we've talked about before was overlap of atomic orbitals or hybridized atomic orbitals creates bonding. And so it's this shared space between the atoms. And so we have our orbitals centered on atoms. Now, they're great for explaining geometry, but that's only one piece of the puzzle. So it talks about the shape of the molecule very nicely. It does not explain things like atomic spectra, or whether a compound is magnetic or not. And so really what it's tying into is it doesn't really tell us anything about electron energies in these orbitals. So the energy of the electron that is associated with that orbital, we can't explain it with anything we've talked about before. And so there's more to it. And MO theory by itself also doesn't explain everything. The truth is actually a mix of the two when you get in like really high-end computational chemistry. That's what we're doing. So this is going to be another piece of the puzzle. So you just get pieces. You don't get the whole picture in this class, unfortunately. So there's two types of molecular orbitals, bonding and anti-bonding, because of course, right? I guess sometimes they're also called non-bonding, because why not? So bonding orbitals, or molecular orbitals. So these are going to be orbitals that are spread over multiple atoms, 2 or more. And so a bonding orbital will be something that's spread over as much of the molecule as possible. It helps hold the molecule together. So that electron is being shared all over the place and helping hold it together. And so they favor the molecule staying in one piece. But we also have these anti-bonding orbitals. And as those fill with electrons, they favor the molecule falling into pieces. And so when you see an anti-bonding orbital, and I'll make sure to do a screen capture where I show these images and talk about them and differentiate between the two. I can't really draw them on the board, but an anti-bonding orbital is going to favor the molecule falling into pieces because it's going to only cover small parts of the molecule, not the whole thing. Now, you're not going to be expected to like draw any molecular orbitals. This is something that a computer has to calculate. This is computational stuff and nothing else. Like this is not something you do by hand, so don't worry about that. It's going to be more kind of, we're going to talk about MO diagrams here in a minute, and also just kind of being able to recognize visually a bonding from an anti-bonding orbital on site. And we'll also talk about the highest occupied molecular orbital, also known as the HOMO, and then there's the lowest unoccupied molecular orbital, the LUMO, and I'll talk about those when I bring the diagram in. So first I've got to erase my board. And so, some quick editing. We'll be back with MO diagrams. All right, I'm never gonna stop using that editing trick. Okay, so MO diagrams. This is what they look like. This is, again, the simplest molecule, so that's where we're gonna start. So we have one electron in a 1s orbital. We have another electron in a 1s orbital. So there's an H over here and an H over here. And then we have bonding in the middle. That's what we're showing here. And so as we can, I didn't write the scale, we often don't, but this is an energy scale. So energy goes up as we go up our axis here. And so this is a lower energy, making it a bonding orbital. We call this a sigma. This is a sigma bond. Write that out. So sigma is kind of like single, might be one way to remember that. It's like a single bond. And so both of these electrons, these are our atomic orbitals. So these are the electrons we're going to use. So we fill this out first, and then we bring it in here. And so I'm going to have one spin up and one spin down because I can't have the same spin in the same orbital. We got this new molecular orbital. All right, and so that is our MO diagram, but that's the simplest possible case. But what we have is a stable molecule. We have 2 electrons in our bonding orbital. It's being held together very nicely. There are no electrons in our anti-bonding orbital. As we fill the anti-bonding orbital, it becomes less and less stable. And so if there were 2 extra electrons we pitched in, it would fall apart according to MO theory. That's what it's saying. If we fill our anti-bonding orbital as well, the molecule dissociates into pieces. But this is very stable. So the more electrons we have that are in stable bonding orbitals, and the less we have in unstable anti-bonding orbitals, the more stable the molecule will be. And it should be no surprise that H2 is a stable molecule. We've talked about it enough times. You know that it is a molecule that holds together nicely. All right, so, What about more complicated stuff, right? Again, I'm kind of ducking out on p orbitals. So we got more complex atoms with p orbitals. Okay. Well, here's the extra detail. You know, if both of our sides have p orbitals associated with them, our p orbitals, they're going to combine to form, we get a, make sure I get this right, you know, we get a sigma, you know, if it's like a 2p, so we'll say our 2p orbitals combine to form sigma 2p, pi 2p, pi star 2p, and sigma star 2p. These are all orbitals. Okay, and these are bonding. And these are anti-bonding. Okay, so we can, you know, look at an example here. So let's look at an element that has p orbitals. And so we did H2, so let's do O2. All right. Now, we're going to have electrons in our 2s orbital. We're only going to work with the valence electrons, so we don't worry about the 1s orbital anymore. Those stay behind. And then we have our 2p orbital over here. And then on the right-hand side, we have our other oxygen with our 2s and our 2p orbitals. Okay, and our s orbitals are going to do just what they did before. We're going to get a sigma and a sigma star bond, so bonding and anti-bonding. And so this is sigma 2s star up here, and this is sigma 2s down here. Okay, and I haven't put any electrons in play yet. We're just going to diagram this out first. Okay, and then we get a sigma 2p. And then we get 2 dashes here. We can hold 4 electrons in our pi 2p orbital. All right, and then up here, we get pi star 2p. Whoops, that'll be 2 dashes as well, excuse me. And then all the way at the top, the highest energy of all, sigma star 2p. Now, you know, if there's any problems with these, you're going to be presented with this diagram. These are computationally determined. There is no order you have to memorize. You just basically have to work with a blank slate like this. And you go, oh, it's O2. And then you just look at the valence electrons. So I have an oxygen over here. I have an oxygen over here. And if I look at my periodic table, I go, okay, well, the 2s orbital is full. Little chapter 7 review here on this side. We're going to work on the left-hand side first. And then we look, we go, it has 1, 2, 3, 4 electrons. 1, 2, 3, 4 electrons in the 2p orbital. And guess what the other oxygen has? It's all the same stuff, right? It has the same electron configuration. Same diagram over here. So these are just the electrons we're starting with. We haven't talked about where they go in the bonding structure yet, but essentially what we do is we just fill up. So I have 2 electrons on each side, up, down, 2 more, up, down. So I had 2 4 electrons, now I have 2 4 electrons in the bonds. They're all accounted for. So that's good. So this is not being held together by sigma 2s bonds, according to MO theory. Looks like all of our bonding is going to occur with these p electrons. So I have 2, 3, 4, 5, 6, 7, 8 electrons. So I just go 1, 2, that's full. 3, 4, again, just like before, I want to avoid pairing until I have to. 5, 6, 7, 8. Okay, I used all 8 of my electrons. All right, and so when I look at this, I go, I have 2, 4, 6 electrons that are bonding, or if I want to include down here, if this cancels out. I have 2 bonding, 2 anti-bonding, so we're not going to worry about that. But I have 2, 4, 6, 7, 8 electrons total, and of those, 2, 4, 6, make some room here. I have 6 bonding electrons, and I have 1, 2 anti-bonding electrons. Okay? That's going to be key, because that's going to let us talk about the bond order. So 6 minus 2 is 4, so I have 4 extra bonding electrons. I have 4 more bonding electrons than non-bonding electrons. So my bond order, this is kind of like, what type of bond are we looking at? That's the MO theory version of that. And so what we have is, if we remember our Lewis structure, we go O, double bond O, lone pairs. So what we are looking at is a double bond. So we'd expect our bond order to be 2. And so it's going to equal number of bonding electrons minus, do parentheses here, so bonding electrons minus number of non-bonding, or anti-bonding, excuse me, anti-bonding electrons, and we're going to multiply that by 1/2. And so we get 6 minus 2, which is 4, divided by 2. It's going to equal 6 minus 4 times 1/2 equals 2, which is what we expect. That means we have a double bond. So there's nothing unexpected there. That's what we're looking at. Now here's the other detail that we can get from these diagrams. And that is, I'll make some room over here. We don't need hydrogen anymore. Unpaired electrons equals magnetism. So remember I said the MO theory can predict magnetism. Well, unpaired electrons equals magnetism. And so, or I should say paramagnetism, it will respond to a magnetic field. Para. So O2 is paramagnetic. And what we'll say is more unpaired equals more paramagnetic. So the more of them there are, this is why, earth metals or whatever are so popular. Rare earth metals are so popular for very strong magnets like neodymium or whatever. I can't remember the name right now. Those are very magnetic because they have a lot of unpaired electrons. And it turns out that O2 is a little bit magnetic. So I have a video on the Moodle page where someone pours liquid O2 between 2 very strong magnets, and it sticks there because it responds to the magnetic field. So it turns out that O2 is paramagnetic. It responds to a magnetic field. It sticks to a magnet. Now, as air, it's bumping around with a ton of kinetic energy. It doesn't happen. That's why the person that does this demo does it with liquid oxygen to show this off. And so these diagrams are key because they can tell us a bond order. They can tell us whether, it's a single or a double, or maybe somewhere in the middle. Maybe we have some resonance, so it's like a 1.5 bond. That will show up in MO theory. The other thing is we fill. So when you work with these diagrams, you want to fill in the atomic orbitals on each side first. They might not always be the same element. It could be like NO or something like that. And I'll throw a practice worksheet out there for you to work on this. All of this will be given to you blank. You do not have to write what the orbitals are called. And then you work the outside, and then you just fill from the bottom up. That's all you have to do. So, nothing too crazy. All right. So, one more thing to talk about. I will also, like I said, somewhere in this video, maybe I've already done it, I will do screen capture. I'll show what these orbitals look like as well. This idea of pi orbitals, very important as well. We'll talk about that in a little bit. In fact, I'll do that next in this video. That's what you'll see next. And then I'll cut back to the board. I got one last thing to talk about after that. So hang in there. We're going to talk about pi orbitals, sigma orbitals, what those look like, what those mean. We've talked about bond orbital, magnetism. And again, this is, oh, actually one more thing. The electron configuration. It's just like chapter 7, except now we've got some new stuff to work with. So this is a sigma, we just work our way up, sigma 2s2, sigma star 2s2, sigma 2p2, pi 2p, I got 4 there, so pi 2p4, and pi star 2p2. Okay. So it's just like chapter 7, just make sure you use these orbitals. So you're not saying like 1s2, 2s2, so on and so forth. Now you're using, you use the molecular orbitals. So be aware of that. And we just go in the order that they fell. We just go right up the line. All right. So yeah, so now we'll splice in that, I'll cut away to that screen capture. We'll look at what these MOs look like, what a 2p means, where it is physically, what a bonding orbital looks like, what an anti-bonding orbital looks like. And then we'll come back and we will talk about conduction bands. So how MO theory deals with semiconductors and conductors. All right. So now we're going to look at a little bit of screen capture of these 3D representations, and we'll get back to the whiteboard lecture here in a minute. But first, we're going to talk about what these bonding and anti-bonding molecular orbitals look like in general. What are their general features? And a sigma and a pi bond, what does that mean? Well, it means pretty much the same thing as hybridization, but we'll talk about it in MO theory a little bit. And so the example I'm going to use for this is benzene, because it's a really cool example. It's a 6-carbon ring, and then every other bond is a double or single bond. And so we got 3 double bonds, 3 single bonds, and so this is a structure that has resonance, because I can move all my double bonds. I could just shift them, one position clockwise, and all the single bonds would be left behind, and that would be the same molecule, and it only would have moved electrons. And so this is something over here in the 3D representation, and its geometry is flat as a pancake, and what we actually have are not double and single bonds due to the resonance, but everything is kind of like a bond and a half. And so it's a really stable molecule, and it's got some really cool molecular orbitals because of this. And again, you don't have to necessarily memorize this or anything, or totally understand it, because there's some higher level stuff at play here. But it's just a really good example for molecular orbitals. And like I said earlier, bonding orbitals, bonding MOs are going to hold the whole thing together. Anti-bonding are going to start having it break into pieces. And so I found a figure on the internet here, and this just has to do with, the pi molecular orbitals. So we're not worrying about the sigma molecular orbitals, but sigmas, just like hybridization theory, those are single bonds. Pi bonds are going to be above and below, and so the magic really happens with benzene with the pi bonds. And so if you look at this bottom one here, this is a very strong bonding orbital because it holds the entire thing in one piece. And then we have the next strongest, well, it holds it in 2 pieces. And then, you can break into pieces this way or this way. So now we're getting into anti-bonding orbitals, because this is going to start favoring electrons only being centered around specific atoms. So this one is totally anti-bonding. Every single carbon would break apart with this configuration. And that's what you're looking at, is just, is it a molecular orbital that spans the whole thing in a stable fashion, or does it start chopping up into pieces? And that's really the difference, is just, does it
start chopping into pieces. Half is okay. That's, you know, that's pretty bonding, especially when it's not going to overpower this bonding orbital. It's already full. But just be aware that you know, chopping into pieces, anti-bonding, holding it together, bonding. That's what we're talking about. And so sigma and pi are just like before. Pi, this would be a pi MO because it is above and below. There's half of it up and half of it down. There's half up here, half down here. That's why these are all pi's, because they're out of the main plane. So in the middle here would be a sigma bond. So there are sigma bonds along the whole way. And so anti-bonding sigma bonds would again just favor breaking of that sigma bond. And so again, it would just favor breaking into pieces. It wouldn't hold stable. You'd see a cleave in the middle. It wouldn't be one continuous space that's holding it together. It would be something where there would be a space of disconnection, just like we would be seeing here with these pi orbitals. And so that's the difference between a bonding and anti-bonding orbital. And we've already talked about pi bonds, the sigma bonds, and hybridization, and the general idea holds true. Just now we can have bonding and anti-bonding versions of them as well. All right, so we'll get back to the very end of molecular orbitals, or molecular orbital theory on the whiteboard here.
All right, so the last thing we're going to talk about, and this is just kind of an interesting thing to discuss. This is, you know, we all use conductors and semiconductors. I can't make this video, I can't post it on the internet without them. We use them all the time. And so MO theory is a very good tool for explaining this. So I figured we'd talk about it. So what we have is, I'll be very general here, but in a semiconductor, this is something that will conduct electricity, but only when we want it to, only a little bit. So what we have, you know, it doesn't just conduct anything, but we have this kind of increasing level of energy, and we have a valence band, and so we have a series of molecular orbitals here, and then there's a jump. So these are all different levels, energy levels of you know, molecular orbitals, and there's a jump. So if we can get enough energy in an electron, it comes up here, and we call this the conduction band. And so this is really key for how, like, solar panels work. So a photon has to come in, boom, it hits an electron that's in the valence band, and it puts energy into it. The electron absorbs the energy of that photon, and if that photon has enough energy, which we can tune, we've gotten pretty good with semiconductors, we can tune this band gap. There's an ideal spot to put it where we'll get the most energy out of the sun. It jumps up, boom, in the conduction band, and then essentially that's a wire, and we just run it off and we use it to power a camera or something. So that's what we have there, and so we call this jump right here, this is our band gap. And that's the energy we have to put in an electron to get it in the conduction band. Once it's in the conduction band, it takes off. It just, boom. It's like the length of the circuit. All right. Now, if we have something like a metal is just a standard conductor. So this is just a normal conductor, which is good. You know, we use metals for things like wires. It's nice that they conduct electricity. It's very helpful. All right. And so we have the same thing. We've got an energy diagram here. And what we have is no band gap. We just have a series of MOs. And so our valence and conduction bands overlap. So we don't have to put a bunch of a bunch of energy into an electron to get it to run down a wire. We don't have to put that much work into pushing it around. Now, in this situation, this is good for something like a solar panel because it can capture that energy. We can get that energy out of it, and it relaxes back down into the valence band. But over here, we don't want to put a bunch of work into moving electrons around. We just want them to move in the wire. That's what that band setup allows us to do. And we can actually run this sort of system in reverse. Instead of exciting the electron, we can use some other source, like electricity, to have excited electrons, relax them through a semiconductor, and release light. And that's how an LED works. So it's a solar panel that runs in reverse. And this is how MO theory explains that. So this is kind of a little fun end of the video. So, there was a lot of stuff here. MO theory is very intense. So just hang in there, work on the practice worksheets. Like I said, you don't have to anticipate the shapes of orbitals, just know what they mean. Is it bonding, anti-bonding? Know how to fill in the diagrams. You don't have to write them from scratch. That would be cruel because again, you need a computer to tell you, well, what goes first? The pi 2p or the sigma 2p, like which one goes on top? Those can shift. So it just depends on what you're working with. So what you get is a blank slate that you have to fill in. All right. So, hope the class is going well. This is the end of our second chapter. And as always, just email me or please use the forum on Moodle if you have any questions. I'm happy to help.